Hey everybody, my name is Luis Mesen and this is my final project for PREDICT-454 Advanced Modeling Techniques. For my project, I chose a competition from drivendata.org called Power Laws, Detecting Anomalies in Usage. So energy consumption is trending up, and in general we want to use as little energy as possible. Buildings don't always perform as intended by their designers and consume excess energy or become inefficient or faulty in terms of power consumption. Detecting anomalies proactively can represent a significant cost improvement and environmental benefit. So the research goal is to develop an automatic, quick responding, and accurate fault detection system using advanced modeling techniques. Now the challenges of this competition are that it's extremely large data and it's a bunch of hierarchical time series with lots of missing values. Also, I think I got in a little over my head on this one because the data were also unlabeled, but we still have to hit a challenging evaluation metric. I've never really had to predict blind like this before, so it was definitely a learning experience. In order to meet these challenges, these were the steps I took. Data subsetting was pretty crucial due to the size of the data set. I didn't spend as much time as I wanted to engineering features, but I did use lagging and differencing as well as some other techniques. I used unlabeled prediction techniques such as using anomaly scores through an auto machine learning pipeline. I'll talk a little bit more about that later. And I also layered some unsupervised techniques on top as well, on top of the anomaly score approach, which is also something I'll elaborate on a little bit more. Okay, so let's take a quick exploratory look at our data. There were 6 categorical variables, many with several levels, one with over 100 levels, and 4 quantitative variables. Like I mentioned, this was an extremely large data set. It caused me to spend a lot of time trying to optimize my code using GPUs and even cloud resources. But thanks to Dan and Travis for putting me on the right track to data subsetting, this ended up making the problem tractable for me. It's actually a technique that Doc Larry had been advocating for all course long. I combined the training and test set and noticed that only certain factor levels were represented in the test set. And by removing all of the unrepresented levels from the training set, I was able to go from 43 million observations to just 700,000, which is much better, obviously. Also, the levels of my categorical variables went way down, 187 unique meters to 6. I think that's pretty good. So here's a visual representation of the pre and post subsetting. We had all types of meters on the left, but only have main meters, virtual main, and virtual meters in the test set. So we were able to subset the training set by those categorical variables. Also, we only have to worry about office and general types of building activities, where in the training set we had laboratory and restaurants as well. Lagging and differencing were key here because the range of values for each of these time series could vary wildly. On the right, you can see 3 distinct types of time series all represented in the data, and there were even more kinds of time signatures in this. Lagging and differencing can correct for trends and also give the values kind of a reference point within the type of meter that we're looking at, which represents kind of the hierarchy of the time series. I also deconstructed the timestamps into their constituent parts, including morning and evening and even business hours, things like this. But honestly, none of that seemed to matter to any of the models. They only cared mainly about the differencing and the lagging. It seemed to have the highest predictive power. Okay, so I mentioned that the prediction was unlabeled. We're trying to predict anomalies, which is a classification, but only really have regression type target variables. The meters have values that they output, but we don't even have any examples of anomalous meters. We don't have a vector that says whether a meter was giving an anomalous output in the training data. So how can we use regression techniques to predict unlabeled categorical values? So Janetsko, Stoffel, Mittelstadt, and Keim came to my rescue. They present this anomaly score that's shown here. Basically, we're saying that our predictions are either poor because we're bad at predicting or because there's some anomaly. And hopefully it's the latter. But we can't just take the absolute value of the difference between the prediction and the actual value and measure that. Since we're testing several different types of meters, we also have to normalize it. So that's what the average t is, an element of time of the predicted value minus the observed value, absolute value is. It's a normalization using the arithmetic mean of the absolute values within the meter. But there is a downside to this metric. It still ranges from 0 to really infinity or very large, and it's hard to find a cutoff of what is considered an anomaly. So we'll talk about ways to do that a little bit later. To get the prediction, I actually used a bunch of auto machine learning pipelines. By the time I had properly subsetted and feature engineered, time was getting a little bit away from me. So I threw them into some auto machine learning to let them see a bunch of different types of models. First I tried H2O, which is what I used for the previous problem as well. And it seems like GBM models work the best here, but we tested, trained several models, including random forest, deep learning, gradient boost, XGBoost, and then stacked the ensembles. Also, I did k-means clustering just against the values, and that was pretty poor, not really worth talking about. So I also used another tool called Data Robot, and although it also liked GBMs for the problem and found them to be the strongest learners, it actually ended up giving me a much better prediction than H2O did. And I'll show you a little bit about the pipeline to describe why. So here's the landing splash screen. You upload the data and select the value, whatever your value is that you want to target up here in the top left. I chose values here, but I realized later that targeting the difference values was a little bit better, but regardless, this is kind of shows the pipeline. Notice also on the right where it says time-aware modeling. This is a feature I really liked about Data Robot. It's smart enough to give you options to model the time series structure of the data. So here's the data. It shows you all the variables, and you can see that the timestamps have automatically been deconstructed for us. And also in the middle here, we can see that the cross-validation will be performed to specially handled time series. I remember from my first project that you shouldn't just randomly cross-validate time series, you should add folds along a time axis, and Data Robot knows how to do that. Here I select an optimization metric, root mean squared error. And here it's running all these various models on the right. It's currently training a random forest regressor and a gradient boost tree regressor. This is kind of a splash screen showing the models that have already been trained and what their validation scores were. Data Robot also has some interesting output visualizations to compare various model performances. For example, here is a scatter plot of the time it took to score the model versus the validation score of that model. So I guess if time was a constraint that you had, this might be a useful visualization. And finally, we predict our values based on, in this case, our training set, but potentially a test set. And there are, for each model trained, the appropriate hyperparameter tuning metrics and charts, and there's some ability to set this on your own as well. Okay, cool. So now we have our predictions, and we can calculate our anomaly scores. But like I said before, what do we do with them? Which anomaly scores are anomalous? Um, so I chose three approaches. The first was just I kind of had three thoughts at least. The first was just to cut the anomaly scores at a certain quantile. I started very high, assuming that the anomalies were going to be low percentage. So I said, hey, maybe it's 99% a cutoff, and then everything higher than that will be an anomaly. So the score ranged from, say, 0 to 8, the anomaly score on meter 2, and the 90th percentile was 7.5. Then I cut it there and said everything above 7.5 is an anomaly. And this is actually how I got my highest score so far, just using quantiles. I've used, actually the best score is a 60th percentile quantile, which is surprising to me. It actually classifies a lot of these values as anomalies. I also consider doing multivariate outlier detection techniques such as Cook's distance, but I came across a couple of interesting avenues in the literature based on clustering. So perhaps we can use unsupervised learning to cluster the anomaly scores and choose using those clusters. I tried first using k-means and got pretty poor results. The visualization on the left shows the predictions of the cluster, so 10 clusters, 0 through 9, and the ranges of values in those clusters. We could take the ones with the highest anomaly score and mark them as anomalies, but honestly this was pretty poor. There's another technique that I just completed, and I'm getting much better results than k-means. It's kind of intense, so maybe if you haven't already, put me on 2x speed, because I'm not sure it's super relevant to the course material, but I found it interesting. So here we go. I guess there's a way to transform the time series using power frequency spectrum clustering. This is a signal processing technique that will allow us to group similar frequency spectrum signatures together and label the ones very far from the group as anomalies. Let me switch to Jupyter Notebooks to continue. All right, cool. So this is the power spectrum frequency clustering for anomaly detection. And the reference is from this paper, Data Analytics for Managing Power on Commercial Buildings by Gautam, Manish, Martin, Jeff, Cullen, and Amip. So we have some preparation steps here. We're importing the training set. And then we subset. I'm going to just subset by 1 meter just so that we can go through an example here. But in the clustering that I did, it loops over all of the meters, which there's 6. But here we're just going to select 1 meter. And basically we group by date. The clustering has to be done by date. We can actually probably set the unit of time equal to anything we want, but I haven't implemented that fine-grained detail yet. The training set has observations every 30 minutes for some of these time series. All right, so we group by date, and then we have a sum of the value that was recorded by that meter. And then we compute the fast Fourier transform based on this formula here in order to compute the frequency spectrum of the power time curve. So like I said, that's a signal processing computation, and it gives us 2 values for this power signature. It's a magnitude and magnitude and phase. Yeah. So we only need the magnitude for this study. We don't care about the phase. So that here you can see an array of 2 columns. The first is the magnitude and the second is the phase. So I just grab the magnitude, and now I have my x, and I want to compute a dissimilar, so this is an x for every one of the days for that meter. And I want to compute a dissimilarity matrix using Euclidean distance. This is a linear algebra transformation using the L2 norm, and the formulas here. So I borrowed this function to calculate the Euclidean distance matrix. So now we have a matrix of m by n dimensions, where m is the number of days being observed, and this is the Euclidean distance between all the frequency spectrum magnitudes. But m by m is way too high of dimensionality. We can't really cluster or do anything with this matrix directly. So we have to reduce the dimensionality of this matrix, and we use manifold multidimensional scaling for this, which is implemented in scikit-learn. So that was pretty straightforward. Okay. So you can really reduce it to however many dimensions using this technique, this multidimensional scaling. It should be low. It should be a low dimension, just because we're going to run k-nearest neighbors later, and we know from the course that the curse of dimensionality holds here, and we want to keep the dimensions low. I chose 3 just because it was kind of cool to visualize, and unfortunately I'm realizing now that these visualizations that we see here, these are the embeddings of the MDS, the multidimensional scaling. So now we've reduced that m by m matrix into this 3-dimensional matrix here, or it's actually 3 by m, or m by 3. And we can plot kind of each of the embeddings, which you can't see, they're pretty small, but there's little ticks here that show the embeddings of now this power frequency. And we can use that, and it's 3 dimensions, so we can also plot it in 3 dimensions. We see a little cluster here, and one guy way out here. And if we zoomed in here, we would be able to see some more like kind of detail in the clustering, or the space between the various points. But what we're going to do is we're going to try to find the k-nearest neighbors for all these points, and then using the k-nearest neighbors, we actually, so here's k. K is selected as a function of basically the size of the embeddings, the m by 3. And then we calculate a function based on the k-nearest neighbors, where this is kind of like a k-nearest neighbors density function. It's k divided by the volume of the smallest hypersphere. So in 3 dimensions, a hypersphere is a sphere. In 2 dimensions, it would be a circle, and in 4 dimensions, it would be some crazy, indescribable thing. But that function, you might remember this. This is the volume of the sphere. So we find the distances from k-nearest neighbors. So here we have each point, and the distance to itself, of course, is 0, and then it goes up to its kth neighbor, and that's the distance. This is the distance to its kth neighbor. And then we find the smallest hypersphere that would contain all those guys in there, and that's our f hat. But f hat is just a prediction of whether the density of these k-nearest neighbors is close or far. We want to transform that into a probability that it's anomalous, and we do that by this function here, where we take the f hat and then we divide it by the maximum of 1 through m of f hat. So that's done here, and we can see our probabilities. This is a rug plot that's showing that there's a lot of probabilities that are low here, and then we start seeing some guys that are above maybe 50%. We might want to pick a 50% threshold here, and we see some guys that we might think that they're anomalies, just because they're far from the k-nearest neighbors density area, or the high density area of the k-nearest neighbors. Yeah, so we add that as a kind of a prediction, and here's a time series kind of depiction of that, and again we have a probability here, so maybe we pick a threshold of 5, and we see that it peaks over that in a few days. Now what I ended up doing is attaching those days to the predictions, and then using kind of both in my final determination of if the observation was anomalous or not. So I'll switch back to the presentation. All right, so again, we have here the steps that I just described. So you compute the frequency spectrum, you compute the dissimilarity, then you want to bring it down to a lower dimensional embedding, and then you use k-nearest neighbors to kind of generate a probability score that it's an anomaly. So more to come on that. Unfortunately, the contest rules, you can only submit 2 per day, and I've hit that limit, so we'll see how it goes. Next steps, currently I'm hovering around the top 10% with a score of 0.2016. It's not a great score, but it seems to be a fairly challenging problem. There's not a lot of people above me, so just I think I'm in the 54 or 56 now. So next steps would be feature engineering, some more lagging or differencing, potentially using exponential smoothing, just because if the 7-day differencing is taking a pretty huge chunk of the predictive capability in my models, and if the previous week's observation was also anomalous, then it might think it's not anomalous just because 7 days ago it was anomalous. So we'd want to probably get some further history in there and average it or smooth it somehow. Some more data cleansing. Because of the data challenges, I didn't do as much of it as I'd like to. Potentially some imputation of missing data. And more on the clustering of the frequency spectrum. I think that I haven't 100% captured that technique, so there's more to learn there, but I found it interesting, so hopefully you did too. All right, thank you for your time and good luck.